So welcome to the first colloquium of spring 2022. We're pleased to welcome back one of our own. Nate Kaib has a BS in physics from CWRU. He wrote a senior thesis on diffuse intracluster starlight under the supervision of Chris Mijos. He did his doctoral work at the University of Washington and postdoctoral work at Northwestern, and is now on the faculty of the University of Oklahoma. He works on the formation and evolution of planetary systems, both that of the sun and of the stars. He's written a number of interesting papers on planetary systems in binary stars, long period comets, the dynamics of the Kuiper belt and Oort Cloud, and using CMB observatories to look for trans-Neptune objects. He's a recipient of an NSF Career Award, and he also has an asteroid named after him. So welcome, Nate. The floor is yours.
Thanks a lot for the introduction, and thanks for inviting me today. And so I guess I'll get started with my talk. So yeah, this talk is basically about what I was working on this past fall at Case. And the title is Comet Fading Begins Beyond Saturn, and it's a paper I submitted at the end of October, and it's been in review, but it's been accepted. It actually got accepted last week to Science Advances, and so it should be out. I can't put the newest version on archive because of embargo stuff, but it should be out sometime in March. Here's an outline of my talk. So I'm gonna, this is a physics colloquium, so I assume most of you probably don't spend as much time thinking about the solar system and orbits as me, but I'm gonna give a brief primer on this stuff. It's all pretty, I'm sure you've heard all of it before, but it's nice to all be on the same page. And then I'm going to focus in on one part of the solar system, in particular the Oort Cloud, as well as long period comets, which come from the Oort Cloud. And I'll discuss their dynamics and some of their properties. And then I'm going to focus in on a very specific class of long period comets called distant long period comets, and discuss evidence for their fading, and I'll talk about what fading means in this talk, and then I'll finish up with some conclusions and potentially future work if time allows. Here is just a cartoon diagram of our solar system. Of course, we have the sun at the center, most massive object, and we have four rocky inner planets in the solar system, the Earth being a third planet out, and then we have four giant planets in the outer part of the solar system. And of course, the solar system is comprised of more than just the planets. There's lots of small bodies. And so closer to the sun, we have two different large reservoirs of small bodies. We have the asteroid belt, which sits between Mars and Jupiter. And we have the Kuiper belt, which sits beyond Neptune. And so the asteroid belt is comprised of small rocky objects. The Kuiper belt is comprised of small icy objects. And within planetary astronomy, we want to know the distances of things, and so the unit that we use is the astronomical unit, 1 AU. By definition, that's the average distance from the Earth to the Sun, and so the Earth sits 1 AU from the Sun, and the distance from the Sun to Neptune is 30 AU. So we're moving out a factor of 30 when we move from the Earth out to Neptune, and so the most distant portion of the solar system I discussed in my first little cartoon overview was the Kuiper belt, which sits beyond Neptune. It sits about 40 to 50 AU for the most part. But if we take even a larger view out, we get to a much more distant reservoir called the Oort Cloud. So the distance units on this diagram here are in AU. So the Oort Cloud, unlike the other two small body populations, which exist as belts or disks, the Oort Cloud is spherical in distribution, and it sits between roughly 1,000 and 100,000 AU from the sun. So this is roughly halfway to the nearest star system. So it's much further from the sun and much more tenuously bound than the rest of the solar system is. And so when we're talking about the Oort Cloud in this talk, I'm going to primarily be discussing the orbits of Oort Cloud bodies. So there's a couple different properties of orbits I want to go over. These are, from basically freshman level physics. We have orbital eccentricity. So this is effectively it describes the degree of circularity of an orbit. So eccentricity runs from 0 to 1, and eccentricity of 0 corresponds to a perfectly circular orbit. And as eccentricity approaches 1, the orbit gets more and more elongated. If it's an eccentricity of exactly 1, it's actually a parabolic orbit. And if we have in a moderately eccentric orbit, now the sun does not sit at the center of that ellipse. Instead, it's offset. It sits at one of the foci, and as an object moves around the sun in the orbit, the distance between the sun and the object changes because the sun's not at the center. Well, actually, even if it was the sun, it would still change. But anyways, so there are two different quantities I want to talk about here. I want to talk about the semi-major axis. So that's half of the major axis of the ellipse. If you average over all angles, this would be the average distance between the body and the sun over one orbit. And then there's also a distance of closest approach, and that's called perihelion in the case of an orbit around the sun. And we use a lowercase q for perihelion typically, and a lowercase a for semi-major axis. So the last orbital element that I want to talk about is the inclination. So the orbits of the planets of our solar system all lie in roughly the same plane, but that's not true of many of the small bodies. So an orbit defines a plane in three-dimensional space. And if you measure the angle between the plane defined by any given orbit and some fundamental plane, in this case, the orbits of the planets, that angle is known as the inclination. Okay, so now moving back to our solar system, so one of the classes of small bodies in our solar system are comets. These are effectively small hunks of ice that are sublimating due to being heated up from the sun. If we plot their inclinations versus their orbital periods, you get a plot like this. And generally, historically, comets have been split up between short period comets, those with periods shorter than 200 years, and long period comets, those with periods longer than 200 years. And short period comets are believed to come from a portion of the Kuiper belt called the scattered disk. And they tend to, and one of the reasons we believe that they come from the Kuiper belt is because they have low inclinations. So they come from a disk-like source. I'm not really going to spend much time talking about short period comets today. Instead, I'm going to focus all of my talk on long period comets, which come from that much more distant reservoir, the Oort Cloud. This reservoir was first proposed by a paper in 1950 by Jan Oort. And so now I want to specifically talk about the Oort Cloud and long period comets. So again, just to repeat this little diagram here, the Oort Cloud is much further away from the sun than any other part of our solar system, and observing it directly is effectively impossible. Most of the objects that comprise the Oort Cloud are of order a kilometer in size, and they sit thousands of AU from the sun. So we have almost no hope of observing them directly. And all of our evidence from the Oort Cloud comes from long period comets. So this is a small fraction of Oort Cloud objects that get into orbits that take them near the Earth and the sun. And to explain the existence of these bodies, because they're both dynamically and physically short-lived, we need to invoke some large reservoir of material around the sun. So the way that Oort Cloud objects get into near-Earth orbits is the reason that they get into near-Earth orbits is because the Oort Cloud is the only reservoir of our solar system that's significantly perturbed by the rest of the galaxy. So if you're an object orbiting the sun at thousands of AU, the sun's gravitational hold on you is very tenuous, and it's easy to be, you're very sensitive to external perturbations. And so there's two main perturbations that affect the orbits of Oort Cloud bodies. The first are passing stars. So, as the sun orbits the galactic center, so do lots of other stars, and they have motion relative to one another. So they have close encounters with one another. And when a star flies past or comes near our sun, it exerts a torque on orbits that are around the sun. That torque can cause the perihelion of an orbit to move, and that shift in perihelion is random depending on the details of the stellar encounter. And so some encounters can pull the perihelia further away from the sun, and other encounters can push them nearer to the sun. Now, occasionally you'll have just the right configuration of Oort Cloud orbit and stellar passage, where you will drive an Oort Cloud orbit to a very high eccentricity, to the point where its perihelion comes into the inner solar system. And at this point, this object, which has been sitting in an extremely cold portion of our solar system for billions of years and is made of ice, comes near the sun, gets heated up for the first time, again in billions of years, and begins to sublimate, and we see a comet in the night sky. And So that's one of the ways that we get long period comets from the Oort cloud. There's also another perturbation on the Oort cloud, which again comes from the galaxy, but it comes from the larger scale gravitational potential of our galaxy. In particular, it comes from the gravitational potential of the Milky Way's disk. So here's a 2-mass image of the Milky Way's disk. If we zoom in on one portion, we can imagine we have the sun and we have an Oort cloud body, and they might have slightly different heights above the midplane. And so as a result, they'll feel different accelerations downward. And this manifests itself in the solar system's frame as a tidal acceleration. And so this is a non-Keplerian acceleration in addition to the sun's gravitational pull. As a result, orbits under non-Keplerian accelerations are not going to move in closed ellipses. And so this causes the perihelion as well as the inclination actually of Oort cloud orbits to oscillate with time. And this can also drive new long period comets into the solar system, into the inner part of the solar system. And so for the first 35 years of our realization that the Oort cloud existed, we thought the only perturbation were stellar perturbations. And so it wasn't until the mid-'80s that people realized, oh, that the tide of the Milky Way's disk is important too. And it turns out that if you actually work through the math and use a reasonable estimate for the density of matter in the Milky Way's disk, you find that the perturbation on the Oort cloud due to the Milky Way's tide is about twice as strong as stellar perturbations. That's on average. So occasionally you can have very strong stellar perturbations because that's a stochastic process, but the tide is there's much less variation from one epoch to another. Okay, so as I said, all of our evidence for the Oort cloud's existence comes from long period comets, and we've been finding long period comets for over 100 years. And here's a plot of all the long period comets that have been discovered since the year 1900. This is from a 2017 paper. And what's being plotted here are the perihelia of the long period comets as a function of their year of discovery. And what you'll notice is that for the most part, they're all in the inner few AU of the solar system. The vast majority of these have perihelia of 4 AU or less. And that's for a couple different reasons. One, it's easier to see things that are nearer to Earth. The other reason is that as comets approach the sun, they get hotter, they sublimate more, which if a comet is more active, it's brighter too. It's easier to spot active comets compared to inactive comets. So there's this very strong function of discovery probability as increasing increasing as perihelia decreases. And now if we just take the comets that are in the inner 4 AU of the solar system that have been discovered with perihelia less than 4 AU, and we plot their semi-major axes, we see that the semi-major axes are not evenly distributed. We see that there's a huge range of semi-major axes. They run from hundreds of AU up to 100,000 AU. But what you'll notice here is that there's this prominent spike between about 10,000. The actual peak of the spike is between 20 and 30,000, but the number of comets really ramps up beyond about 10,000 AU in semi-major axis. So this is what is known as the Oort spike. Again, this is pointed out in Oort's 1950 paper. And based on that paper, we've taken to calling all long period comets with semi-major axes bigger than 10,000 AU. We call those new comets. And the reason is that as was argued in Oort's original paper, and as I'll explain, we are pretty certain that new comets, ones with semi-major axes bigger than 10,000 AU, are newly arrived from the Oort cloud. They're making their first passes through the inner solar system. And so the reason that we're pretty certain that those are new comets and the rest are not is because when an object passes through the inner solar system, on its way into the inner solar system, it's going to interact with the outer planets. Namely, it's going to interact with Jupiter. It's going to feel some perturbation from Jupiter. And as I already said, these objects, these Oort cloud objects or long period comets, are extremely weakly bound to the sun. So they have orbital energies that are just below zero. And so even just the slightest perturbation from Jupiter is enough to eject these objects onto hyperbolic orbits. The alternative is if Jupiter doesn't eject this object. So in that first case, Jupiter gave the comet extra energy and caused it to leave the solar system on a hyperbolic orbit. Jupiter can also take energy away. In that case, it shrinks the semi-major axis dramatically, and you wind up with a comet with much smaller semi-major axis. And so long period comets are generally divided up between new comets that are, again, have semi-major axes bigger than 10,000 AU, and then returning comets, which have semi-major axes less than 10,000 AU. And it's generally believed that returning comets are simply new comets that avoided ejection on their first passage through the inner solar system, and then they return on a more tightly bound orbit, hence their smaller semi-major axis. And so just using only 19 comets, actually, Oort noted that that the group, the semi-major axes beyond 10,000 AU are overrepresented compared to what you'd expect. And so this is what caused Oort to surmise that the Comet cloud, which we now call the Oort cloud, must extend beyond 10,000 AU from the solar system. Now you notice, there's the number of comets in the Oort spike drop off once you get to 10,000 AU as you're moving to lower semi-major axes. So a natural question to ask is, does this mean that the inner boundary of the Oort cloud is at 10,000 AU? The answer to that is probably not, for a couple different reasons. So when we see a long period comet in the inner part of the solar system, its perihelion has to move from some large value to some small value. So imagine you have an Oort cloud body that's destined to become a discovered long period comet. Its perihelion, before we ever see it, was likely in the outer solar system, somewhere in the outer solar system. And so it made a pass, it makes perihelion passages in the outer solar system. In order for us to see it, to actually discover it as a long period comet, what has to happen is, in a single revolution around the sun, the perihelion has to move from somewhere outside Saturn's orbit to somewhere inside Jupiter's orbit by the time this thing goes around the sun again. If that happens, then we can discover this object as a long period comet. The reason that's necessary, the reason that particular criterion is necessary, let's imagine that doesn't happen. And so we have this Oort cloud object, and it makes a perihelion passage somewhere exterior to Saturn. But unlike the first example, the perihelion evolves more slowly. And so the next time this object comes through perihelion, it's not in the inner solar system, but it's, say, somewhere between Jupiter and Saturn. At this point, this comet, it's unavoidable that this comet will receive significant perturbation from Jupiter. As a result, it's very likely that it will leave the solar system on a hyperbolic orbit, and it will never get the chance to evolve to a much lower perihelion that will allow us to easily discover it. And so this effect is called the Jupiter-Saturn barrier. And it should be, well, it's really called the Jupiter barrier, but it's basically Jupiter blocks a lot of comets from entering the inner solar system because their perihelia don't evolve quickly enough. And so because the gravitational barrier posed by Jupiter and Saturn, it's required for long period comets to have a very rapid rate of perihelion shift. We know from just basic orbital dynamics, though, that the rate of perihelion shift depends strongly on semi-major axis. The further you are from the sun, the more sensitive you are to these external perturbations. So as a result, even if there are lots of objects in the Oort cloud that are orbit, inside of 10,000 AU, their orbits just don't evolve quickly enough. So this prevents comets from entering the inner solar system if they have semi-major axes below 10,000 AU. So this explains why new long period comets have, why there's this steep ramp up at 10,000 AU for new long period comets. But this doesn't fully account for the Oort spike. It does part of the work, but it's actually not enough. So again, this is what the observations look like. We have new long period comets and returning comets, and so the Jupiter-Saturn barrier helps to explain that left side part of the spike, but the spike is still not prominent enough. You can simulate this process pretty easily in n-body relations. You populate the Oort cloud, and you allow the galaxy to drive the perihelia of Oort cloud bodies into the inner solar system, and you can simulate the production of long period comets. And so I've done this in several papers, and just as a toy example for this talk, I did that. And this is the distribution you get if you simulate the production of long period comets with, the galactic perturbations as we understand them, as well as the planet's orbits. So it looks different. You see an Oort spike, but it's much less prominent than in the observed data. You can see that there are, if we look at the number of comets at semi-major axes around 1,000 AU, they vastly outnumber, in the simulations, they vastly outnumber the ones that are around 20 or 30,000 AU, whereas it's the opposite in the observed. There's more comets with semi-major axes at tens of thousands of AU than a few thousand AU. So this has been known for a long time. And in fact, Oort and Schmidt in 1951 wrote a paper noting that Jupiter and Saturn alone cannot explain how prominent this spike in comet semi-major axes is. And what they concluded, and what the general consensus of the field has been ever since then, is that new comets making their first passage through the inner solar system are much more likely to be discovered than returning comets. And this intuitively makes sense, because each time a comet passes near the sun, it sublimates material off of its surface. The reason comets are so easy to see is they're sublimating material, and that produces this, very prominent tail, and it also pulls dust off, which reflects sunlight. And so as comets make multiple passages by the sun, they probably deplete their near surface volatiles, and they just have a smaller inventory of materials to sublimate. There's also a camp of people that, comets have also been observed to fragment, and there's camps of people that believe that fragmentation causes this, but and the fragmentation again is driven by solar heating, but there's some process that causes comets to physically age and fade. That's the generic term given for this during successive perihelion passages. As a result, returning comets just simply aren't as bright, and it's easier to miss them. And so our general idea for the evolution of a comet that we see from Earth is that it first makes a passage in the outer solar system, somewhere in the outer solar system. Its perihelion evolves quickly over the two gas giants, Jupiter and Saturn, and then it comes through, and we see it as a new comet. And after that passage through the inner solar system, if it's not ejected, it's drawn onto a much smaller semi-major axis by the perturbations from the gas giants. And this time, on this returning orbit that has a smaller semi-major axis, instead of it being instead of it having a vigorous amount of activity like its first passage, it has a suppressed activity. It's not quite as easy to spot, and it comes through, and we are less likely to discover it. And so comet fading in the inner solar system has been parameterized in a lot of different papers, and the most successful parameterization is tying the discovery probability, or the comet survival, to the number of passages that the comet has made within a certain distance. And so this is a paper from a couple of years ago by Colloquium and all, where they show that the distribution of long period comets from the Oort Cloud can be well explained if the probability of comet survival is simply the number of passages it's made within 3 AU to some power. And again, that's not observationally motivated. It's an empirical fit to the observations. But the key here is that the number of passages, n goes up, n pass goes up every time there's a perihelion passage inside 3 AU in this paper. Some other papers use 2 AU. And so this in fact makes physical sense. There's a motivation for this choice of distance, because we know from observations with small bodies that water, and as well as just simple physics, that water begins to sublimate around 2 to 3 AU in the solar system. And it's thought that water is the driver of comet activity. Sublimation of water is the driver of comet activity. So you're going to deplete your near surface water eventually as you make more and more entrances inside the inner 2 to 3 AU of the solar system. So this is the state of the knowledge we can derive from our long period comet catalog, our current long period comet catalog. So the current sample, because it's dominated by comets that are in the inner few AU of the solar system, the current distribution of comet orbits is greatly distorted by fading, as well as the Jupiter-Saturn barrier. And so the current sample of long period comets tells us that the Oort Cloud exists, but it really provides limited information about the Oort Cloud beyond and like the details of its structure. And so for a long time, it's been thought that a sample of long period comets with perihelia outside of Jupiter, so near or beyond Saturn, which in this talk I refer to as distant long period comets, they should be much less affected. They will definitely be less affected by Jupiter's perturbations. And since they undergo less heating, they should be less subjected to cometary fading. And so I did my I did my PhD thesis on formation of the Oort cloud, and in that thesis and my papers that I wrote, I wasn't the first person to write this. I said it's going to be great when the VRC Rubin Observatory comes online, which it will in the next 1 to 2 years. So that they will that observatory will be imaging the entire night sky every few weeks. It'll be great at finding very faint things that move around our sun, and we'll build up this great sample of long period comets with perihelia well beyond Jupiter. So that's been, most Oort cloud and long period comet papers will end with some kind of statement like that. So that's exciting because it's coming up. But I kind of got interested in what we can say right now in the last few months. And so I started looking. I mean, I was aware that there are some distant long period comets that are known, as you can see in that plot. And so now I'm going to switch gears and talk about distant long period comets as well as evidence for their fading. So if we return to this 2017 plot, you can see that we're getting better and better at finding comets with distant perihelia. So there's this, if you look at the upper bound of the red points, it increases over the decades. And in particular, since the year 2000, we've found in this plot, at least we found, I think, 8 comets with perihelia beyond 8 AU. And just for reference, Saturn semi-major axis is just inside 10 AU. And so these are comets that are well beyond, and Jupiter's at 5 AU. So these are comets that are well beyond Jupiter and near or even exterior to Saturn. And that was in 2017. If you go into the JPL small body database now, we now know of 25 comets, 25 long period comets with perihelion between 8 and 12 AU. So, that's not a massive sample, but go back to Oort's paper in 1950, that was based on 19 comets. So we're getting not great at finding these comets, but we're approaching being okay at finding long period comets with perihelion out near Saturn. So then the question is, what can we do with these? Well, the first thing you can do is plot up their orbits. And so just to refresh your memory, so this is what the distribution of orbital semi-major axes of comets entering the inner solar system look like. So you have this prominent Oort spike on the right, and then you have the returning comets on the left. So my first thing I did with the sample of comets is I just made an analogous plot for the distant long period comets. And this is what you see, which is pretty crazy, I think, because what you'll notice is the Oort spike doesn't disappear. In fact, it's even more prominent among distant long period comets. This is completely opposite of what you'd expect if fading due to water sublimation is what is driving the prominence of the Oort spike in the near long period comets sample. And so this is really unexpected. And so that raised the question, well, is there something funky about Oort cloud structure? Because, like, as I said, the long period comet sample, as we know it, doesn't really put a tight constraint on the distribution of comets in the Oort cloud. So what I did is I designed an Oort cloud to be really good, to basically optimize the structure of the Oort cloud to be really good at producing long period comets with tens of thousands, with semi-major axes of tens of thousands of AU, and be bad at producing long period comets with semi-major axes less than that. So I basically, just populated an Oort cloud with semi-major axes between 20,000 and 50,000 AU, uniformly distributed. And then I evolved this for 2 billion years under the influence of the galaxy as well as the giant planets. And then I, looked at the orbits of objects that pass, that are long period comets in my simulation that pass near Saturn. So with perihelia between 8 and 12 AU. And I compared that with the observed data. And so that's shown on the left here. So the simulated data is the cumulative distribution plot marked with red dots, and the observed data is the thicker gray line. And so you can see that this simulation fails horribly. It predicts that 96% of distant long period comets should have semi-major axes below 10,000 AU. In reality, only 24% of them do. So this is a really bad match to the observed data. And the problem would be much worse, actually, if we used a more plausible Oort cloud structure where there was stuff orbiting inside of 20,000 AU. And so what I found is that really, even with best case scenario for what the structure of the Oort cloud looks like, you cannot replicate the observed long period comet orbits near Saturn without invoking some sort of fading. Otherwise, you're just dominated by these returning comets instead of the dynamically new ones. And what I found by just by basically turning the knob on how quickly fading occurs is that in order to successfully replicate the semi-major axis distribution, the fading must happen quite rapidly. And so this is an example of a successful fading law where the blue line, the blue dash dotted line, is simulation data. It's the same set of bodies that produce the red distribution, but I've just allowed them to only make us a limited number of passages. And in fact, for the blue simulation data, those comets disappear from the simulation after when they exceed 5 passages inside 20 AU. So that's just 5 passages inside basically the orbit of Uranus. And so this is pretty surprising. One, because it happens so fast, but two, as I said earlier in this talk, comet fading, if you go back through the literature, it's always tied to water sublimation, but this fading cannot be due to water sublimation. It can't be dependent on water sublimation because water is not going to begin sublimating at 20 AU. And so that's surprising, I think, as well. And so the general idea here is that to explain the observed comet sample in the outer part of the solar system, basically comets come by. The first time we can see them prominently, we detect a comet with a perihelion near Saturn. The next perihelion passage through the comet has now depleted, or is less active. I think it's presumably because supervolatiles are driving this, but anyways, so this second time through, it's less active, less bright, and we see it where it's much harder to detect. So that's why those smaller semi-major axis ones don't show up there. So if this rapid fading is real, we can actually make a prediction on the behavior of comets that's a little analogous to what we talked about in the inner solar system. If comets can only make a handful of passages through the outer solar system, that basically sets a short timer during which we can actually observe and detect a long period comet. And so what that does is it requires the comets that we observe, that we discover, they should all have perihelia that are moving sunward and doing so rapidly. And we will miss all the slowpokes, the ones with perihelion moving really slowly, or the ones that are moving backwards, say they had perihelion near Jupiter and moving further away. We'll miss them before we're able to discover them. So the idea is that if a comet's perihelion is moving in slowly, makes a passage, say out near Uranus or something like that, and then by the time it gets close enough for us to see it, if it's moving slowly, it will have already been faded, and we'll miss it from our observing campaigns. And similarly, if you have a comet move way into the into the solar system and back out, that takes a lot of time too. So if a comet goes in and then comes back out under perturbations, it'll make one passage, and then by the time we get to Saturn again, it'll be faded and we won't see it again. And so the only comets that we should be able to see are the ones that are moving unidirectional. So they're coming in they're coming in fast. So then, during this body's march in perihelion space, it only makes 1 or 2 passages through the outer solar system before it's in our zone of observability near Saturn. And so there's this simple prediction of the behavior of these orbits, and it turns out that signature could actually show up in the orbital distribution. And to understand that, I now have to talk about maybe one of the lesser discussed orbital elements. And so I want to talk now, I want to pause and talk about one other orbital element, that's the argument of perihelion. So if an orbit is an ellipse, the position of perihelion can point in any direction 360 degrees in the plane of the orbit. And so the argument of perihelion is that purple little omega angle in this diagram, which marks the angle of the line that points to the orbit's perihelion relative to some reference point. And so the reference plane in this particular example that I want to talk about is the plane of the galaxy. So for simplicity's sake, let's just say that the sun exists right at the midplane of the galaxy. And let's assume that our orbit, our long period comet orbit that we're interested in, is totally perpendicular to both our line of sight as well as the plane of the galaxy. So in that case, this would be the orbit's argument of perihelion. Now, when you have very eccentric orbits like this, they basically spend almost all their time in aphelion, or the distance of the furthest distance from the sun. Not all their time, but the large majority of their time is somewhere near there. And so we'll just think about how this body behaves at that position in its orbit. So it has some velocity vector. If we split that velocity vector into its in plane and out of plane components, we see that the vertical velocity, that's the one I want to pay attention to, is moving away from the plane of the galaxy. Now, meanwhile, the tide of the galaxy is in the opposite direction. So as a result, with this particular configuration, the angular momentum of this orbit, and therefore its perihelion, should be decreasing over time. Now let's rotate this orbit a little bit by 90 degrees. And here's the argument of perihelion. Now it's somewhere between 90 and 180. And here's the new velocity vector. And now we can see that near aphelion, the vertical velocity is going towards the plane. And so it's being assisted by the acceleration due to the galactic tide. So the angular momentum and the perihelion should be increasing over time. Now, if we do continue with this rotation, here's the new argument of perihelion, something between 180 and 270. Here's the new velocity vector at aphelion. And so the vertical motion, the vertical velocity is now out of the plane, which is in the opposite direction of the acceleration due to the galactic tide. And so in this case, you're taking angular momentum away and the perihelion is decreasing. And then finally, if we go to the last quadrant, we see here's the argument of perihelion between 270 and 360. Here's the velocity vector when the object is furthest from the sun. And now the z velocity is going toward the plane in the same direction as the tidal acceleration. So the angular momentum increases. And so we have these four different quadrants of behavior, where if the argument of perihelion is between 0 or 90 or 180 and 270, the perihelion is moving towards the sun. Meanwhile, if it's in these other two quadrants, the perihelion is moving away from the sun. And if you actually work out the math of this, what you find is that the rate of perihelion change of any given long period comet is proportional to negative sine 2 omega g, where omega g is the argument of perihelion relative to the galactic plane. So the direction and the speed of the perihelion shift is largely determined by the argument of perihelion. So now what we can do is we can simply calculate this value. It's straightforward to calculate this value for all the known distant long period comets, and we can look at the distribution. And this is the distribution we see. It's highly asymmetric. You can see that there's a really strong clustering of bodies very near sine 2 omega equal to 1, which means that the rate of perihelion change is moving toward the sun, and it's moving basically as fast as possible. And there's nothing on the left side of the plot where perihelion is increasing and moving far from the sun. So now we can compare this again with the predictions of simulations of the production of long period comets. And this is what comes out of the simulations. And you can see there's still this bias towards the red end of this plot, the right end of this plot, but it's not nearly as strong. The reason that there's that bias there is, again, Jupiter's likely to eject things, so you don't want to get too close to Jupiter. But still, you can see that over a quarter of these bodies have negative values of sine 2 omega g, or over a quarter of these bodies have increasing perihelion, whereas the observed, none of them do. And there's also a much tighter clustering towards a value of positive 1. Now, when we can take this simulation, and just like with our semi-major axes that I already talked about, we can invoke comet fading, the same comet fading law. And when I do that, you see that the match still isn't great. It improves dramatically, and particularly improves the degree of clustering towards positive 1 really improves a lot. The fraction of negative value shifts down some, but it's really the clustering towards positive 1 that increases. But remember that that I just kind of made an ad hoc assumption about what the structure of the Oort cloud looked like. So I populated it between 20,000 and 50,000 AU. Now what we can do is we can try alternative distributions of bodies in the Oort cloud. So we can kind of shave off the outer part of the Oort cloud. If we eliminate the outer 10,000 AU and only consider bodies between semi-major axes between 20,000 and 40,000 AU, the fit gets better, or the match to the observations get better. And it gets even better if we get rid of most of our exterior part of the Oort cloud, and we only consider the inner skin, the stuff orbiting between 20 and 25,000 AU. Then it's actually a pretty good fit. And so you can play this game and exclude different ranges of semi-major axes. And what you see, if you just compare the observed data with the simulated data, what you see is that your match to observations just generally gets better and better and better as you decrease the maximum semi-major axis of the Oort cloud. Now, the reason for this is, again, as you get to orbits that are further and further away from the sun, they're much more sensitive to external perturbations. And as a result, their arguments of perihelion fluctuate wildly in just a single orbit around the sun. And so no matter what you do, if you have lots of orbits at say 40,000 or 50,000 AU, you're never going to get a super tight clustering towards +1 in that plot, even if you assume outrageous comet fading of like just a single passage inside 30 AU. And so this is kind of cool. This plot, this distribution of arguments of perihelion tell us two things. One, it supports this idea that comets fade rapidly, and also tells us, it gives some hints about the Oort cloud structure. It tells us that bodies with semi-major axes of 20,000 AU or even less should dominate the production of comets. Okay, and then the last thing we can do is, the other thing that plot tells us is that, at least for the recent history, say the last few million years, the galactic tide has been what's dominating the perturbations on the Oort cloud. It hasn't been dominated by field star passages. The reason we know that is if stellar passages dominated, you'd never expect to see a clustering. There'd be nothing special about that sine 2 omega g equals 1. You'd never see a clustering near positive 1. So that's really nice. That's a really convenient fact, because it makes it much easier to project what comets did in the past few million years. Because as I said, there's not much variation. The galactic tide is just due to the density of matter in the Milky Way's disk. So there's not a huge amount of variation from one epoch to another, whereas stellar passages, their strength can vary wildly depending on what types of stars the sun has encountered. And so this allows us to rewind comets' orbits. We can integrate them backwards within the galactic tide for a single orbit, and we can see where they used to be the last time they came through the solar system. So that's what I've done here. In this plot, I've just taken the known comets, the known distant comets, and I've integrated them backwards in the galactic tide for a single orbital period. And then I've looked at where their previous perihelion passages occurred. So this isn't 100% accurate, but it's a good way to estimate for an ensemble of comets. And what I've found is that of the 25 comets with perihelion near Saturn, 19 of them had a previous perihelion passage beyond 12 AU. And of the ones that did not, of the ones that had a previous, their pre-discovery perihelion passage was near Saturn, they all have semi-major axes below 10,000 AU, and it's consistent with those comets being on not their first time through the solar system, but their second or third or their fourth. And so what this plot suggests is that we start losing comets from our observations. They start disappearing or fading from observability at a minimum of 12 AU. Whatever process that causes them to disappear kicks in by 12 AU from the sun. And so just to as a sanity check, I took my simulated comets in my simulation and back integrated them for a single orbit and compared their distribution, and with the fading law that I've talked about before, and compared their distribution of previous perihelion with the observed distribution, and it's a pretty good match as well. At this point, what I've argued for is that there's evidence that comets fade that distant comets fade in the outer part of the solar system. That evidence comes from the semi-major axis distribution of comets. It comes from their arguments of perihelion, and it also comes from the previous perihelion passages. Up until now, I've just assumed in all of these plots that comets fade after passing through the inner 20 AU of the solar system after just 5 times. But those are free parameters. I have no idea what distance comets begin fading at, and I also have no idea what number of passages are required for a comet to fade below observability. So those are basically free parameters, and the constraints come from those three different properties that I just talked about. So what you can do is you can look at each different constraint. So the semi-major axes, the arguments of perihelion, and the previous perihelion passages, and you can look at what combination of parameters are allowed by the observed data by simulating that particular fading law and then comparing it to the observations. And so that's what's shown in the left plot here. It's the swath of fading parameter space that is permitted by each of those 3 different parameters. And the cool thing about this is that all three areas overlap with one another. And what we can take away from this, if you look at the ensemble or those 3 different areas, is all the evidence suggests that the comet fading has to begin somewhere beyond 12 AU. and comets fade after no more than about 10 passages within 12 AU of the sun, and they can fade potentially in as few as two passages. At that point, they just are beyond our current ability to detect. And so, just to summarize, long period comets with perihelion near Saturn are less affected by Jovian perturbations, and as well as less affected by water sublimation. So this has been a highly sought after group of comets, but when we look at the ones that we know of, they show the same prominent Oort spike that the near ones do, which is very confusing. And so what I found is that the observed orbits that we know of, the 25 comet orbits that we know about, are best replicated if comets fade from observability after a handful of passages within 20 AU of the sun. So this is, our constraints on fading will be dramatically improved in the next couple of years when detections start popping out of the VRC Rubin Observatory. However, it also severely complicates the interpretation of that future data. So it's good teasing out what we know about the Oort cloud from 300 distant long period comets is going to be more difficult because we have to consider their fading. But on the other hand, what we also know is that distant cometary activity has been kind of a mystery in itself. So that's been observed for the past 20 years or so, and it's becoming more and more common. And if we can actually nail down when comet fading begins and how quickly it happens, that may provide insight into the physical mechanisms behind this distant fading, as well as this distant activity. And so with that, I guess I'll just stop here and I will take any questions you have. And thanks again. I see Heather has her hand raised.
Yeah, go ahead, Heather. I guess we'll dive straight into questions. Thanks, that was great, though.
Okay,
Thanks.
Nice talk, Nathan.
Thanks a lot.
Did the Oort cloud just get smaller?
Yes, well, yeah, I think so. I mean, you can't have a lot of stuff beyond 20,000 AU, or maybe 25,000 AU.
I mean, does the calculation, and this is something that maybe I'm just not understanding your simulations properly, but does the calculation take into account how it gets harder to hit the sun from a long way out? Do you know what I mean? A tidal perturbation won't have as much chance of getting there.
Yeah, so that's built into the simulations. So yeah, I agree. You have to reach, for a given semi-major axis, you have to reach a more and more extreme eccentricity to get on like a planet crossing orbit. But that should just pop out of the simulation. So so even if you have a modest amount of material at 40,000 AU, you'll still just get several comets that don't obey that tight clustering in the Argon perihelion. So yeah, I should point out too that this is from an amalgam of different surveys, and it's right at the edge of their detectability. So there is clearly some observing bias in there. But I also find it maybe slightly unlikely that they would, compound each other to give you this tight clustering right where we would predict it from galactic tidal dynamics.
It's a pretty strong result by the look of it, especially with such a small number of comets.
Yeah, thanks. Yeah,
almost as good as Oort,
Thanks. Yeah, I mean, I hope it's real.
Oh.
Okay, so I see Paul had his hand up, so maybe we'll go to Paul next.
Yeah, just turning this completely round the other way. What does it say about the early solar system and the given that the super volatiles are important in the fading, properties of the protostellar disk and how early these got kicked out and from what radius?
Yeah, actually, let me go back to my talk for a second. Did I close it? Hold on. Sorry. Yeah. Somehow I've lost the window when I'm trying to share. Well, I'll just tell you that that was part of one of my future work slides. So, the general consensus is that the Oort cloud is a product of planetesimal scattering in the early solar system. So the giant planets scatter material out. Most of it gets ejected, but some of it gets trapped in this spherical halo around the sun. And so one interesting thing about that is that that material, the best case scenario is that that material formed at 25 to 30 AU. and was scattered out as Neptune kind of plowed through it. But Neptune doesn't do most of the scattering. It's so Neptune dislodges them from circular orbits, but they have perihelion excursions down to Saturn or so. And so I want to actually do a follow-up work where we revisit the formation of the Oort cloud and, look at what fraction of bodies make repeated excursions inside, 15, 10 AU, and does that work with this fading law, basically? And I don't know if it would or not. I mean, the sun would be slightly cooler at that point, and so that might help you. Yeah, I think there's implications potentially about our model of how the Oort cloud formed.
Thank you.
But I don't have an answer.
All right, so before we go to the next question, I just wanted to explain that if you have questions, you can use reactions to raise your hand, or you can just put it in the chat. And especially welcome questions from students, so go for that. Also, I guess the process is that we'll probably have questions for a few more minutes in this formal session. But then after that, we'll have Nate's kindly agreed to stick around for a little bit longer. And so we'll stop recording, and then we'll have, just conversation off the record. So opportunities to talk there also. Okay, so the next question was Chris. Do you want to go ahead, Chris?
Yeah, yeah, so Nate, in your model you had with the galactic tides, right? You had the simple model where the sun is at the midplane, but the sun's a little off the midplane, and even more than that, it's bobbing up and down. So,
Yes.
So is that enough of a difference from just the midplane approximation that it kind of smears out the hope that you're going to see those correlations?
Yeah. So those oscillations do matter, because what matters is the local density, say a couple of parsecs around the sun at any given point. And so if you modulate that, you're going to modulate the strength of the galactic tide. And so in my tidal model, I don't actually assume the sun's at the midplane. I assume it's occupying a portion of the disk with a density of about 0.1 solar masses per cubic parsec. Now, that can increase and decrease. And people have done work on tide by about a factor 4. But that clustering, even if you vary the tide by a factor of 4, that clustering, it should still be there. I mean, it matters, but I don't think it's going to change the shape of these distributions too much at all.
So it'll smear it a little bit, but it won't make it go away. Okay.
Yeah.
Okay. Thanks.
Okay, go ahead, Stacy. I guess you're next.
Okay, thanks. So this is related to Paul's question, and I'm really curious about the mechanism for fading for these things that stay out beyond Saturn, because as you said, I have pounded into my head that you get inside the ice line, and that's when you start to lose water as a volatile, and that's when you see it. So what could be going on to make something fade further out? Is it methane?
Well, I mean, so yeah, I think I think comet fading by itself is still poorly understood, like conventional, but because there are camps of people that believe it's all fragmenting nuclei, and so you just turn a big comet into smaller comets. But I think the depletion of near surface volatiles is a very plausible thing, and so we have discovered over the last 15 years or so, and it's becoming more common, comets active at extreme distances out at 20, 25 AU, and it's not clear if that activity is powered by a transition between from amorphous ice to crystallized ice, because that can release some heat and it can drive activity, or it can be powered by super volatiles like CO or something like that. Where was I going with this? Oh yeah, so I could imagine that there's actually two types of fading potentially. So there's the type that has been documented that occurs around 2 to 3 AU, but then there's a earlier phase where you say deplete your surface CO or something like that, or you deplete your, you convert all your amorphous ice to crystallized ice or something like that.
Okay.
But I mean, those are just guesses. I think it's a poorly understood process, but there's clearly something's driving this activity and it goes away fast.
Yeah, that's kind of shocking too, right? Whatever this unknown new process is, works pretty well.
Yeah.
Okay, are there more questions from students, especially? I guess I have a question. I'll ask the ignorant physicist question. Is there any prospect of directly observing Oort Cloud objects? You know, not when they come in as comets, but like out there. I remember there was chatter about maybe using occultations of stars, and some of these are not that far out. They're only a few thousand AU. So.
Right. Yeah. So there was a proposal that didn't get selected for a NASA Discovery mission back in, I don't know, 2014 or something like that, to have a space-based campaign to look for distant occultation that could have directly detected Oort Cloud objects out to at least a few hundred AU. And then, so there's that. And then there's also a little different variety. There's an ESA mission that's being developed called the Comet Interceptor that will, so this is basically finding a long period comet, or sending a probe to a long period comet as it's entering the inner solar system, which would still be really cool because we get very little heads up on these objects. It's not like short period comets where they're predictable for decades in advance. So this was designed in with an interstellar comet in mind, but it could very easily be used to study new long period comets as well.
All right, well, that's pretty exciting stuff. So perhaps this might be a good place to stop the formal proceedings, and then we can go on and chat informally. So thanks very much. This is a great talk, and I'm afraid Zoom doesn't allow us to express that adequately.
Thanks a lot for having me. It was fun.
Yeah. All right, well, don't go away though. We're just going to stop recording.